Good evening. Tonight's workshop's on the introduction of 3D design using Onshape for FTC teams. My name is Brad Damaso, and I'm mentor for the last 4 years for Minerva's Mechanics. Minerva's Mechanics is a FTC team with Brunswick High School in Brunswick, Maryland. We're in Frederick County. There's only 3 teams, FTC teams in Frederick County. And for the last 4 years, been pushing the kids to learn CAD. And in the last 2 years, we've been focusing on using Onshape. We really like Onshape because of a number of features that include, it's a fully featured professional CAD software. It has a lot of features that really fit with a team trying to produce a quality engineering notebook. It's a cloud-based system, so there's no software to install. It uses a Chrome browser, so it's like a Google Docs of CAD. It's cross-platform compatible, so you can be on a Mac, you can be on a PC. You can log in at home, you can log in where your team is working on building the robot, and you don't have to be lugging around a heavy-duty computer that has a big install of software on. You're able to access your file from anywhere. You can even use it on a cell phone. Probably the biggest thing is being able to share a single CAD document that encompasses the whole design of our robot with all the details, engineering details, product details, simultaneously across the team. So it's a collaborative effort to produce a CAD model of a FTC robot, and we can have 5 or 6 kids or even more logged in at a given time, working on the model, producing documentation from the CAD model for the engineering notebook. If you're an FTC team, you can get a free educational account. You can go to onshape.com/educational and get an educational account. I highly recommend it. They do have what's called a free account, but a free account does not allow you to share documents. You need an educational account to be able to share documents. So that's what you need for a team, is an educational account. And it's become very popular amongst first teams. A lot of FTC and FRC teams are now using Onshape. So with that, I'd like to switch over and continue the introduction into the details of producing a model in Onshape. All right. Well, why don't we now just jump into Onshape here and look things over here.
Brad, have you turned off the view option and stopped the?
I've turned off the allowing participants to annotate, if that's what you're saying.
Okay.
That sounds good. Thank you.
So let's see if problem keeps going or not. So with Onshape, the biggest thing for an FTC team is the ability to have one common document that you can edit and work on across your whole team simultaneously. So we, on our engineering notebook, use Google Docs. So all the team are simultaneously editing and contributing and adding content. Onshape is no different. So that's the beauty of the package, is that it allows for a collaboration amongst team members that you're not going to get with some of the other free software, CAD software out in the marketplace. So some of the things that we find that are really important to us as an FTC team is we're always hemmed in on the size of our robot. Is it really going to fit into a sizing box before we actually build it? And will the designs actually make sense from a sizing perspective? So some of the unique things that we do, and I'm going to tell you some of the better practices, best practices that we utilize with Onshape here for a few minutes, is we create a virtual sizing box. So we have on the screen here our robot from this past season. The robot, we've put it into a 18 by 18 inch square box that's 14 inches tall. And you can see that with the current modeling, that we're protruding out the back here a little bit. We can also fine tune that a little bit, go and look at different views of the robot and try to determine exactly which parts and how is it that we can move things around so that we fit within our constraints. When you design, you're always designing with constraints. Constraints are a good thing because it makes the whole project, you know, have boundaries, makes it easier to think about things. So we always try to map out on paper what all of our design constraints are. And from there, a lot of times what we can do within those boundaries, within those constraints will fall out. So the other thing that we do with our Onshape modeling is we like to organize our single document into folders. So on the left-hand side, we see a whole long list of folders. Those folders will have multiple things. First off, we'll have sub-assemblies of the robot in their own folders. Below all the sub-assemblies of our we then have our parts. We happen to use a combination of Actibotix, Andy Marks parts. Everybody uses Rev Hubs. So all of those parts are on the websites of the manufacturers or the sellers, and you can download their CAD files. I think everybody kind of knows that by now. So we like to organize our CAD files into the Onshape, much like you're going to see the Actibotix webpage, so that everybody in the team has an easier way of finding things. So we have things in motion components, structural components, and it just goes right on down the list. So if we come up here and we look at the Servo City website, selling the Actibotix parts, you know, they got motors, motion components, structural components, electronics. So we try to mimic as a best practice, we try to mimic what we're seeing on the website so that it's very easy for the team members to move back and forth between downloading the CAD files and importing it into the Onshape so that they're ready to then do assembly and design. So the other thing that we also like to do is we like to download, as you see, the plane pieces from Andy Marks, get their CAD files, so we can then work with figuring out how many skystones high is our design realistically going to stack. And so we're replicating then the match play with our robot. We take advantage with Onshape of the Onshape's ability to replicate the motion of the robot that we're after. So here we're able to expand and contract our slides. This is our cascading slide mechanisms for the lift and the extension. We go in and we try to carefully create those linear motion of those components. so that we can use that to simulate how the robot is going to interact with the plane field elements. So those are some of the things that we do in Onshape with the team. You combine that with a collaborative effort that one can achieve, and it becomes a very powerful platform for everybody. So I taught a class, it's a 3-hour interactive class with for other rookie teams here in Maryland. And so I've put together this class, and I'm trying to pare down the class into about a half an hour here after and kind of show you some of the ins and outs of how you assemble things in Onshape and some of the finer points of Onshape and how it impacts your FTC team. So in CAD, the first thing you think about is you're designing parts from scratch. So what I want you to think about is not designing parts from scratch, but assembling parts from your parts kit first. Everybody's bought Go Build a Actibiotics kits, Tetrix kits. You're going to download and import those into Onshape as if this is what you choose to do. So the first thing that you're going to run up against with Onshape is it's got way more features available to you than what you could probably figure out in your lifetime. So let's talk about what is important. We know that we're working with a parts kit. So let's start with the parts kit. I've put into this file, again, motion component, structural component, shafting, just like I would in a team document so that we can start assembly. So in Onshape, it's 3D. So we got to talk about the fact that there's a front view, there's right views, there's isometric views. I think that should be pretty self-explanatory. You have to think in all 3 dimensions at once now that you're in Onshape. Now, with Onshape, there's a part studio, and then there's an assembly studio. A part studio is where you create geometry, and then the assembly side is where you put those parts together and create your robot. So the first thing that we're going to do is let's create an assembly from scratch. You're going to take, and because I've preloaded my content with the parts that we're using today, I get a list of parts in this that I can grab a hold of and insert. So we're going to put a shaft on the screen, a shaft spacer. We're going to grab an assembly over here. We're going to grab a bearing, and we're going to grab a hub so that we can create an axle assembly that will allow us to then put wheels on a robot. So in Onshape, they have a system where you use fasten mates to assemble everything together. So you have fasten mates that are static and that they just go together and they stick like glue, and then you got ones that revolute, so they rotate, so you can mimic the rotation of a shaft. Then you have linear fasten mates, so you can replicate linear motion. So what I'm doing here is I'm using a fasten mate to just glue a D hub onto an end of a D shaft. They're Actibiotics parts, and I should have pointed out to you that because we have that D flat, I did not pay attention while I was talking to the fact that I needed to rotate that so that the flats mated. So we'll talk a little bit as we go about some of the nuances of the fastening system here. I should mention that with the mouse clicks, you're able to zoom in, rotate, do all that kind of stuff. So with a fasten mate, we're now going to put that little black washer, Actibonics washer that goes against the inner race of a bearing onto the shaft. So notice on this fasten mate, as I touch on the circle, I get a little coordinate system and a datum point on the screen. So that's the z-axis, that's the blue line. So you're wanting, so the direction of that blue line is important. As you move around the part, you're picking up different pieces of geometry and you're creating different datum points. And so what we're doing is we're trying to match the datum points up and in the direction that makes sense. Now notice in this particular case, and this is, you got a 50-50 chance of getting this right the first time, that the washer is actually on the back side of the surface where I want to place it. So you just hit the arrow and you pull it out front. So now you have your washer on the front, the way you go in life. So now I'm going to grab hold of a bearing, do the same fasten mates thing here. And again, the bearing is on the back side where it should be, and we just flip it with the arrow and away we go. So now we have an assembly. And once you have an assembly, what's important is to start thinking about how that assembly is going to be documented in an engineering notebook. So we're going to create a BOM table real quick and looking at the parts used in the this axle assembly. So it shows up and it shows an item number, a quantity, and a part number, and there's nothing populated in there. Well, that's because we want to add a column based on name. So let's get rid of where did it go? Well, so much for that quick, important. That's not showing what I need. All right, let's move on. We'll catch it on another assembly. So once you create an assembly, a sub-assembly, you can then now start to create robot frames. And so here we've taken channel, we've linked it all together, we've put axle assemblies on, we've put wheel assemblies on, we've put sprockets on, and we've created a very simple push-bot type frame. So let's see if, there we go. So here we do an assembly. Within the assembly, you can create the BOM table, the bill of materials table, and this one is actually showing up correctly. So we're using the part name of the individual components in the column for the bill of materials. It's automatically figuring out the quantity, and it's giving us item numbers. So notice down here that we're getting a lot of the same numbers here. And this thing called flattened and structured assemblies. And so one of the downfalls of importing all these parts from the websites is they'll come in as let me get a wheel here real quick. So if you import in an Omni wheel from Servo City, this is the number of parts within the file. And these parts have to be put into an assembly. So now we're going to open up an assembly. And once these parts are put into an assembly, they now have one and only one unique name, and that's, Omni Wheel Assembly. The problem is these parts, when they get imported in, they have to be grouped together. So I'm going to turn off I'm going to remove the group feature here for the moment. So you have 21 individual parts that come in from your CAD import, and they end up as unique parts that are unstuck to themselves. So you have to group them together when you import these assemblies so that when you grab a hold of them, you grab a hold of the whole thing at once. So 90% of the problems that you're going to run into with Onshape is this problem alone. And that is when you import parts that have more than one component to them, you have to create an assembly and then group them together. And then that assembly, then it can be used to build further assemblies. And then when you move everything around, it all stays together. So here's another great example, are macadam wheels. Macadam wheels have about 50, 60 different parts. This is a part studio that was imported directly into Onshape, and we're now going to create the assembly of that macadam wheel. We're going to have to first insert the macadam wheel into the assembly. Notice there's still individual components. You need to select everything, group it, and now when you select it, it goes as a unit. So that when you now go to let's go back to this folder here, to this chassis. So now when we go back and we want to do an insert, so one of your dilemmas is do you pick the macadam wheel that's a part studio, that's all the individual pieces that will move around on you, or do you pick the macadam wheel still generating a preview that is all one entity. So you got to keep that all in mind, and that has a bearing on your bill of materials. So if you go to the flattened structure, the flattened structure gives you every individual component that's in that macadam wheel and in that Omni wheel. So there's 95 total parts that are in this chassis. If you do the structured bill of materials, there's only 12 parts, and that's more realistic. Why is this important? Well, you want to try to get an accurate bill of materials for your engineering notebook. You're required to produce a parts list for your engineering design journal. So you want to utilize the capability of Onshape to create your part list automatically. You can take all the parts, all the bill of materials from your sub-assemblies, and you can export it out to a CSV file, put it into Excel, and clean it up. And now you have a highly accurate parts list for your notebook. But it's only going to be accurate if you understand the difference between a part studio having all these individual parts that you've imported in on a macadam wheel and putting them into an assembly, which is only one entity. And the other thing is you'll notice that that name really doesn't mean anything to us. So let's go ahead and edit that. Is it Andy Mark, macadam wheel, and I think it's the right side. So you can go in, edit your part name, all within the bill of materials. And over here, you'll now look, our assembly now has the updated name. So that's the one nice thing, one of the nice things about Onshape is everything is highly interlinked together. So I see my time is ticking away. So I would, as a suggestion, I would start practicing with your assembly. Once you get assemblies down, then you can start designing parts that are unique to your robot. So if you were to design a new part, you're going to create a part studio. It's in 3D. The first thing you have to do is you got to sketch something in 2D, and then you got to extrude it. So we're going to create a sketch. We're going to sketch on this top plane. We're going to go view normal to the sketch plane. We're going to grab a square. We're going to dimension it 2 inches by 2 inches. We're going to grab another square, dimension it 1 inch by 1 inch. That'll be the sum total of our 2-dimensional sketch. Now we're going to extrude. And if we click on the exterior of the sketch, we quickly create a 3-dimensional object. It defaults to a depth of 1 inch. You can obviously update that. And so now we have created a 2-dimensional object. If you want to add further geometry, it's the same process again. We want to put some holes on the top of that part. We create another sketch plane on the top of that part. And I don't think it picked up the top, so let me try again. There we go. So what I want to do is I want to add a couple construction lines. I'm going to put a point in the corner. Dimension that to be 1/4 inch. And that comes out a little funky. That's not what we want. So that's why you get the redo, undo. Quarter-inch. So that one didn't take. So now it's like any kind of CAD system. You can mirror. Your points. And then with the points mirrored, let's exit our sketch plane. Now let's pick up on a we'll pick up on the whole feature. One of the things that I don't like about my small screen laptop is it bunches everything up. And then it changes it around on kind of a little bit random at time. All right. Why did that just up? There it is. That's what I'm after. So we're going to pick up on these holes here. So this is a great thing. If you put points on the surface, and you can make you set the diameter of the hole, you make it a through hole. Note, if you get the angle just right, you can see all the way through. But sometimes if you're going to 3D print this part, you might want to create a counter bore for a 632 screw, which is the size of everything that we use on Actibotics. And you can create counter bores to go along with your through holes for your screws. So this part now, we'll consider it finished. So we can, let's say we want to 3D print it. So we go export, you give it it defaults to it, the Part Studio 1 name. You want to pick an STL file format for spitting out the 3D printer compatible file. Most slicing software likes things in metric and preferably or usually in millimeters. So with that, you've now created a 3D file that you can then go and print, see whether or not you obtain the geometry that you're interested in. So there's a lot of training tutorials out there for drawing, and so there's no way to go into a lot of that stuff tonight. But I'm going to give you at the end, I've got to delete that macadam wheel because that gets carried through all my all of the balance of my exercises here. So when you're running autonomous, you're wanting to put a lot of sensors on your robot chassis to use the sensors to drive the decision making and your autonomous programming. So a typical one is to use a color sensor on the chassis to detect the blue or the red tape on the floor of the playing field. So if we wanted to take and put a sensor onto a chassis and make a 3D custom-made bracket to hold it, it's quite straightforward to do an Onshape. And in this particular example, what I want to do is show you the ability of doing what they call design in context. So we're going to take the Rev color sensor, insert it into our assembly. Notice that the sensor it's on its side. Here's the side that the connector is on. You want to keep in mind when you orient your parts and design, you can't model in your wiring, but you got to factor that in mentally. So this part needs to be rotated into the right orientation. It's not necessary to do that because when you do the fasten mates, it would go ahead and take care of that for you. But I like to do that because it makes it easier to get the fasten mates right the first time. So now we're gonna mount this. We're gonna orient this sensor in the center of the C channel and into the front of it. So this here is a unique. This is how I would do that. We know we want to go into the center of the channel, so it automatically is picking up the center of the channel for me. And notice that I oriented that datum so that it pointed downwards. I'm going to come down here. I'm going to catch the back edge of that sensor. And I've now fastened that sensor edge to edge to the center of the robot frame. And this is an intermediate position. That's not where I actually, want the thing in the long run. So what we can do is we go in here, and this is very important to be aware of, is you can edit that fasten mate with offsets. So we look, there's the Z-axis, there's the Y-axis, so the X-axis is going back into the page. So I want to move this thing minus 0.25 inches. It's positive. So that we now have it a 1/4 inch ahead of the frame. When we look at the, it's probably about 5/8 of an inch off the floor, so that's a good height for it to accurately read the color off the tape as you travel across it. So now we have the sensor where we want it. Now you want to make a bracket that mounts the sensor to the frame. So the way we started was trying to drilling and bending metal, making custom little brackets to mount all the sensors, because the hole patterns really never lined up exactly where we wanted them to be in life. And because this is a rev part designed in metric, this is Actibotics, it's designed in inches, so the hole patterns never match. So it's always an annoyance. So what we're going to do is we're going to design in context. So we have this sensor where we want it with respect to the C channel. We're going to use the geometry of the mounting holes in the sensor and the mounting holes in the C channel to create to create our geometry. So we really don't have to get a ruler out and measure anything. And we go create part studio in context. The first thing it wants is the origin or mate connector. Well, right now we haven't done that yet. So we're going to use a mate connector. I'm going to add it to the center of that hole. And sometimes you got to zoom way in order to catch the geometry that you want. We now have a mate connector. We come down here, we're going to create a edit in context using that as our origin. So that's going to create a part studio. So this part studio is just like all the other part studios that you're going to see, except superimposed in that part studio is the geometry that you're trying to mate to, that C channel and that sensor. So what we want to do is we want to sketch. We're going to use the sketch plane is going to be the C channel. And we're going to create a rectangle here. And I'm not being overly exact with all the dimensions. So we create a rectangle, and that rectangle is catching the interface of the sensor and the C channel. We're going to extrude it. We're going to extrude it by 1/4 inch. And notice that it looks like Swiss cheese. It's picking up all the mounting holes of that C channel. So if we go in here and we fill them in by just clicking on them, those will be the 2 mounting holes that we use for our fasteners. So now we're going to create another sketch. The sketch is going to be off the face of that extrusion. We'll make that also make that 1/4 inch high. Let me double check that dimension. I see that I have 15 minutes left and I have haven't let anybody ask questions yet. This is the last little bit that I'm going to demo, then I'm going to start taking questions and see what pops up at this point. So we're now going to extrude that. I happen to know that it needs to be extruded out 1 5/8 inches. Let me get a little bit of an angle. There we go. Nice bracket. Now we got to put the mounting holes in on the back side. Create another sketch plane. This time I'm going to add a point in the center of the hole. And then we're going to go to the extrude, put in a hole, and we're going to use a simple through hole. It's going to be custom. We're going to put in a diameter of 0.16. The reason I use 0.16 is if you use a hole smaller than that on our 3D printer, the screws interfere. That's due to the, the innate inaccuracy of extruding out the filament and trying to 3D print holes. So it's better to print the holes a little bit bigger so the screws slide through. Most everybody's using PLA material. You really don't want to have to come back in with another operation where you take a hand drill and try to drill the hole out or fight the fact that the screws don't go into the hole. So tolerances are a whole nother discussion in life on design that we won't have today, but so here's now our custom-made bracket. It's designed in context to the, click on everything here. Now we go back to our assembly. We can hide our fasten mates. We made a custom-made bracket. We don't really care to know anything about the geometry, but we know it's going to be a perfect fit because we transferred over all the holes from the C-channel and the sensor once we located those two relative to each other. Now, all of those that are looking at this, you're going to say, well, there's a problem down here because you'll never fit a fastener into there and into that hole simultaneously. And that's a true statement. I designed this part just to point that out. We constantly fail to factor in the size of the fastener and how it gets inserted into a part when we're designing our robot. So I just want to bring that to the forefront so that you guys can all keep that in mind. It's a common problem that everybody, I'm sure, has. One of the things that you can do is you can insert the fasteners from a standard content library and model all the fasteners at every joint that you wish to do. We don't do that because the more fasteners you add, that's more geometry, that's more data that's put into the model. So that means the model's open slower. And not everybody has an abundance of memory on their laptops on the team. So you have to balance out, when it comes to fasteners, how many of those you really want to put in. We put them in where it's critical, where we know we have space constraints, and we model them in that way. So with Onshape, you have this tremendous capability to model your robot, model it with respect to the playing fields. This is the end of my quick demo. It's hard to convey as everything you can in such a short period of time. So there you have a learning center where for follow-up, you can go to the training content from Onshape, and the instructor-led classes cost money. The self-paced courses are free. So if you go into and if you look at the fundamentals classes, so if you're wanting to get started in Onshape, you would want to do introduction to sketching, part design using Part Studios, Onshape assemblies, and then I think everybody should do document history and versions, because a robot, you never design everything and put it together and it worked perfectly the first time. So there's always an iteration. So there's a way to handle all those revisions very nicely in Onshape so that you're able to document the whole process and put that into your engineering notebook. So a couple of things real quick that I did not do that I'd still want to do. So here's this bracket that we designed real quick. So if I go and create a drawing, and if I go in and edit the properties and get the scale, correct. We can create an engineering drawing of that part, which should also be included in your engineering notebook. I'm not going to dimension everything here. The other thing that you can do, let's see, that one's probably not going to do what I want, but we're going to go for it anyway. We're going to create a drawing, and we're going to drop in this axle subassembly. And what we want to insert in three-dimensional view of the assembly. We're going to put in our bill of materials. We're going to add we're going to add call outs to that. So what a call out is if you look in an industrial manual, they're going to have a parts assembly diagram. So we have a shaft. It's item number one. Item number one is a part, we have the name of our part studio so that it has the 643080 quarter-inch D shaft, 4 inches long. Part number two, it's an Actibiotics part number. We could go in and add a further description. Part number 5 is a clamping hub, and so on and so on. So you can create some very elaborate assembly drawings that you should create and print and put into your engineering design journal. We call it an engineering design journal. And on our team, it's really the engineering notebook. That's the official name. So somehow or another, I'm kind of finished with the Onshape side of things, and I need to see if there's any questions in Slido that I can answer. So what is the best CAD website? Well, it's onshape.com, of course. I don't even understand that one. That's not, I do not have an Onshape account. I'm a retired teacher. I do not have an educational email address. How do I sign up? I volunteer at 4-H. So you go to onshape.com/educational and you sign up for an educational account. You say you work for, or you volunteer with the 4-H, and they'll give you one. You can also get a regular free account. The problem with the free account is you can't share documents with a team. So you need to have an educational account so that you can share with other people on your team or other people that have Onshape accounts. So I'm getting an email. Oh, no, never mind. That's my daughter. / edu. So here's your educational sign up. Will it be recorded? You might have to leave earlier. I think Heather recorded this. How do you open the FastenMate? How do FTC teams get Onshape? So go to the educational site, onshape.com / educational, open it up, create an account. How do you open the FastenMate? I'll show you that in a second. Let's see what else we got. Is a 3D model made in Onshape compatible with most 3D printers? That's a great question. And so you're creating, so when I do the export, I'm exporting out a .stl file. It's called a stereolithography file. It's a three-dimensional file that gets imported or opened into your slicing software. Cura is a very common slicing software that's out there. We have a Luzbot 3D printer. We use the Cura software. So the model goes into Cura. Cura slices it. That's why we call it slicing software, creates the layers. Each layer gets laid out in filament by the 3D printer. So Onshape models are compatible with 3D printers by exporting out the stereolithography files. And how do you get the precise measurement of each piece? How long is this workshop? Well, it's going to end here in a few minutes. How's that? Have you used other CAD solutions? If so, is there anything, these things keep moving on me, that makes you prefer Onshape for the design other than the collaborative feature? Yeah, so what I like is I'm not stuck on a given computer to do Onshape. I can be on my laptop at the team meetings. I can be on my desktop at my office at work. I can be on my desktop at home in the basement. All I am doing is logging in Onshape and I'm pulling it all up from the cloud. So you can move from computer to computer, Mac to PC. When we get over to the where we build the robots, everybody pulls it up on their various hardware and life goes on. It's great. So a lot of the features that you see in Onshape in terms of FastenMates and designing parts and doing the assembly, SolidWorks is going to do all that too. But SolidWorks is not going to give you this collaboration feature. It's not going to give you the cross-platform feature. It's not going to allow you to share a single file amongst your whole team. And so that's a big one for us. So how do you edit a FastenMate? So if we click on this FastenMate, right click and go edit, we get this dialog box popping up. You click on offset. You can change the offsets in X, Y, and Z. You can rotate or reorient the secondary axis, and you can flip the part in for in. You can see the bearing flipping. We can move that bearing 2 inches up. That's where you get in. You can edit the FastenMates. If there's one FastenMate that's wrong, you can X out of that and make a connection to a different part. So all the functions are available to you to edit after the fact. The other thing is you can come in here and you can rename them so that at some point in time they might be more meaningful to you. So that's a nice thing to do so that your teammate that is also working with you can follow along in the model, is because you've been very careful to get the naming convention on everything spelled out. So let's go back to Slido, see if there's any more. Is camber usually necessary? Can we? All right, so is there any more good questions out there? How difficult is it to make the whole FTC kit pieces in Onshape? How do you import Go Build a part into, all right, so we're not getting kicked off here. So let me show you the process of, so whether it's Servo City or and get, so let's go down, grab a part, any part. So whether it's, you're going down here and you want to get the step file, you want to download that, you want to open that up. That's going to be zipped up. So you either have to do an expansion of that or just go in and cut and paste. So now we're going to go into Onshape. We're going to go down to the plus sign. We're going to go import. I got to back up one level. There's the part. Let it grind away a little bit. And then sooner sometimes they lose the file. Oh, there we go. They on an import, it seems to import it randomly. So here we have the Part Studio. Part Studio has, this is the screw that goes, there's the screw that goes into the threaded hole. And the next is the actual pinion gear. Now we come over to the assembly. Now the screw is in the holes. And the assembly is what you want to be inserting into your models. It's a great example of what I was talking about a little bit earlier, which I know is probably not very clear, is in that assembly, these parts aren't all glued together. So now this will drive you crazy until you perfect this grouping process. Now, if you group that all together, that screw will not pull out of the hole. When you go to an assembly to insert it, it's going to cause mass confusion because that assembly, that part is going to show up in the Part Studio, which is the pieces that are unglued together. And it's also going to show up in the assembly, which everything is glued together and moves as one piece. So let's go to any more. I don't understand what that question is. So how difficult is it to make the whole FTC kit piece in Onshape? That's a great question. So there's two trains of thoughts on that. If you go to other documents, you type in FTC, you're going to find that a lot of teams have spent a lot of time importing various geometry, building libraries, that are publicly available. If you go FTC, Acto, see Got that spelled correctly. You can pull up other people's content and start from there so that you don't have to spend all that time inserting and organizing everything. So that's the easy question. And I know there's teams that they pride themselves on having every Actibotix part ever built imported into their library, and it's available out there. But my suggestion is that your team learn how to do the imports themselves, how to organize the files themselves, because that's then going to teach them what these parts are, how these parts interact, and they're going to get familiar with then the Actibotix or the GoBuilder or the Tetrix websites, so that if they need another part that they don't have, that they know now where to go look and how to find these parts. It's going to teach them organizational skills, because you just don't want to willy-nilly put stuff into to folders. You want to segregate things out. Let me see if I go back to our model from this past year, and then once you start doing this from year to year, you'll eventually build up a very large inventory of parts that are just your own and that you now know for sure are correct. If you start importing somebody else's library, how do you know they didn't modify the parts? How do you know that they're not, how do you know that they're really correct? And so, your mileage will vary as to how you want to handle the importing of your geometry. Any other questions? Okay, how do you measure something? So, great question. And so, let's say I want to know what the length of that is to that. I click on both of those, and it tells me that the minimum distance is 1 inch, 8.75, or 1 7/8. You expand that out, it'll tell you in 3 dimensions what those dimensions are. So what the length is, I can't guarantee you what that number is sometimes. What I find on the measurement tool is if it's a simple part like this, it's going to give you a good number. If you get into an assembly and I want to measure from the side of the wheel to the bolt, to the screw, it's 8.406 inches. But really, what is that number? Once you start to get more complex geometry of more features, it becomes harder to get that measurement tool to land exactly where you want. The other thing is you got to be careful. I clicked here to there, that's a vector. You got to expand yourself out and see what the dimensions are in, X, Y, and Z to see if those dimensions are what you're looking for. And then once you highlight these numbers, you can see it's telling you, it's giving you a dashed line to try to lead you as to what that dimension, where it's coming from. But you got to practice, and you got to check and double check when you do that measurement tool to make sure you're getting really what you want. It can mislead you very quickly.
Hi, sorry to interrupt. I think we'll do just one more question and probably wrap it up.
Search camber, please. Okay. So I showed you only rudimentary design and drawing features. So if you're after Camber, which you seem to be implying that you're interested in how to draw an arc or some sort of a surface, all that capability is in there. You can draw lofted surfaces. You can draw multi-point curves and extrude them out. It's rather kind of endless. So that's what Google's for. You'll be able to find your answer on how to do that in Onshape without a problem. So I had put together, see if I can get back to this. So I think Heather might be sharing some of the PowerPoint slides, not that they're all that much. So I've highlighted on the PowerPoint slides the self-paced courses that I find the most useful for the teams. There's a forum where you can post questions. And then, you know, there's a lot of third-party YouTube video tutorials out there. There's one by, if you search for CAD sessions on YouTube under Onshape, that guy's pretty good at explaining things. So this will wrap up then the quick introduction to 3D CAD using Onshape. And thank you for your time tonight. And you guys have a great weekend.